Welcome to another edition of Math Fun Notes. In this edition, we are looking at these two algebraic structures called fields, q root 2 and q root 3. q root 2 is r1 plus r2 root 2, where r1 and r2 are both rational numbers, and q root 3 is r1 plus r2 root 3, where again r1, r2 are rational numbers. It can be shown quite straightforward to prove that q root 2 and q root 3 are both fields with the usual addition and multiplication operation. In particular, both these sets contain the additive inverse of each element as well as the multiplicative inverse of all non-zero elements. 0 is the additive identity and 1 is the multiplicative identity, and the rest of the properties of fields hold from the fact that these are all real numbers, and therefore whatever other properties, distributive properties are there of real numbers would hold also for the case of these two sets. Now, what is an isomorphism? So an isomorphism from one set to another, say f from q root 2 to q root 3 will be called f is 1 1 and onto, that is f is a bijection, and for x y belonging to q root 2 we have f of x plus y is equal to fx plus fy, and f of xy is equal to fx into fy. So any function which satisfies this will be called a field isomorphism. So this map f will be called a field isomorphism if it is a bijection and it satisfies these two conditions. Now the problem tells us that there is no such isomorphism possible. So we cannot construct a function from q root 2 to q root 3 which will satisfy these properties. And if there is no such function which satisfies these properties, then we say that the fields are not isomorphic. So the fields are not isomorphic if there does not exist any isomorphism. So this is what we are going to prove here. So one of the interesting facts that we can see here is that if we are looking at the elements root 2 minus 1 and root 2 plus 1 and multiply them, so we get 2 minus 1, which is 1, and therefore we would expect that f of root 2 minus 1 into f of root 2 plus 1 is equal to f of 1, and f of an identity in one field is the identity in the other field. Now observe that root 2 square is equal to 2 and 2 is 1 plus 1. Looks like a trivial result, but that's very useful in these kind of arguments. This tells us that f of root 2 square from this property is f root 2 into f root 2 from this property, and therefore this is f of root 2 square. So that is an interesting observation that f of root 2 square, which is f of 2, is f root 2 whole square. So f of 2 is f root 2 whole square. Now f of 2 is f of 1 plus 1, which is f of 1 plus f of 1 by this property, and f of 1 is 1 because 1 is the identity of q root 2, and identity of one field is mapped to the identity of the other field in case of isomorphism. So f of 1 is actually equal to 1, and therefore we get that this is equal to 2. So f of 2 is 2, and that is equal to f root 2. Now is this possible? Let us try to see whether it is possible to have f root 2 square will be equal to 2. So this is the question before us. Now what is f root 2? F root 2 is r1 plus r2 root 3 for some rational numbers r1, r2. So therefore what this equation is claiming is that R1 plus R2 root 3 whole square is equal to 2. Expanding, R1 square plus 3R2 square plus twice R1 R2 root 3 is equal to 2. And we know that this would mean that R1 square plus 3R2 square is equal to 2 and 2R1 R2 is equal to 0. This is from basic algebra. Since 2R1 R2 is equal to 0, that means that either R1 is equal to 0 or R2 is equal to 0. So at least one of them has to be 0. So if R1 is equal to 0, then we have 3R2 square is equal to 2, which means that R2 is equal to square root of 2 by 3. Now, square root of 2 by 3 is an irrational number, so we can conclude R1 cannot be 0. So, since R1 is equal to 0 leads to the fact that R2 is an irrational number, so we can conclude that R1 cannot be 0. Now, if R2 is equal to 0, that means R1 square is equal to 2 or R1 is equal to root 2. Again, we know that root 2 is an irrational number. So, R1 again in this case does not belong to Q, which is a contradiction. So, if R1 is 0, we have a contradiction. If R2 is 0, we have a contradiction. So R1 and R2 both cannot be 0. But in that case, 2R1 R2 is not equal to 0 and we arrive at a contradiction. So there is no element in Q root 3 which satisfies this condition that f root 2 square is equal to 2. Hence, so no isomorphism is possible. Thus, we can conclude that the fields Q root 2 and Q root 3 are not isomorphic as fields. Thank you.